Feel free to interrupt. Okay, I'll share my screen now. Okay, I hope you can see the document. I will have to decrease. Okay. Now, last meeting, if you recall, we ended with integration by parts. Okay, and I have mentioned that before we go to the next topic, I will show to you this formulas. We call this reduction formulas. I hope you could see it now. The reduction formulas, some of which you have already seen and met in the topic under trigonometric transformation, or the integrals involving complex trigonometric functions. So we call this the reduction formulas. They were all derived from the by parts method, which we have discussed last meeting. Okay, so the rest of the examples in by parts, I will clear my marking here. The rest of the examples in by parts, I leave that to you to read, because anyway, the solution is there already, because I already gave you examples in here as per our last meeting's discussion. So we can save time, we'll go straight to the reduction formulas. Now, these reduction formulas class allow you these reduction formulas allow you to answer directly without having to do by parts. Meaning, you need not show the u and determine the du, or you need not show what's the chosen dv and determine the v, and then apply the formula for by parts, which is uv minus the integral of v du. You can directly, again, I will repeat, you can directly use the formulas that you have here, and there are 10. If I may suggest, class, have a summary of formulas within which, when you take the quiz or the exam, that way you will not have to cram. Look for it there in your desktop when you try, if you need that particular formula. It's different if you have your notes. More so, it's very important now in your time wherein you don't see your teachers. It's important that you still have your notes, and you need not rely on the soft copies that you have saved there in your computer. Because should your computer have any problems or technical difficulties in accessing your files, then you will really be entirely lost because you don't have your hard copy. So that's the importance of the Stone Age. I will call it Stone Age because then during face-to-face, students don't rely like 90% on what's available online. They have their notes. So I hope you should have your notes and have these formulas written, because anyway, you are free to access these formulas later should there be a need. So what do you have in here? For example, you are given an integral of u raised to n, ln of u du. So as long as that n is a real number, then this is your answer for that. You just have to follow the formula. If you are given the integral of ln of u raised to n du, then this is the answer for that particular integral. Okay, you need not do by parts several times because it just happened that your ln of u has an exponent other than 1. Now, the exponential function here and the cosine, the exponential function and the sine, this is one of the examples. And you have here a ready-made formula for that. We call this the reduction formulas. So you need not derive them, directly use them. If you can recall, on our topic on trigonometric transformation, you have this, the cosine of u raised to n. You have the sine of u raised to n. As long as that n is not equal to 0, this will be your straightforward formula. Okay, this has no limitation. So in trigonometric transformation, this n could be odd and positive or even and positive, but in here does not have any limitation in this formula in here. As long as it's not equal to 0, this will be your answer. Okay, so you have here another formula. Actually, you have seen this in your trigonometric transformation. So this is a more straightforward formula. Whenever you have a combination of sine and cosine with no limitation, as given in the cases under trigonometric transformation for the exponent of the sine and the cosine. So in here, you can use the formula integral of sine u raised to m cosine of u raised to n du as long as m is greater or equal to 2. So meaning you cannot use 1, 0, and negative. And in here, you can't use values greater than 0, less than 0, because n should be greater or equal to 0. So you cannot use n which is negative. Other than this particular types here wherein you have a specified value for m for the formula to work, you don't have limitations in here anymore. So you can use this formula directly, especially if you have a lot of numbers to process. You can use this formula directly without having to worry about showing your solution. So in the exam, you will be given choices. So it's really important that you have a summary of formulas within reach. Okay, so make your notes and make the summary of formulas that you need. For this afternoon, we will discuss one of the two supposed to be topics that I'll be discussing, but since we only have around 10 minutes, I will go directly to the integrals involving hyperbolic functions. Okay, please take note, class, that you have these identities to use whenever the need arises. So you have these identities relating the hyperbolic cosine to the hyperbolic sine, and the hyperbolic sine of the sum of two values here, x and y, or difference of two values, x and y, as you can see here. Okay, these are your set of identities for the hyperbolic functions. These are your set of identities for the inverse hyperbolic functions. So many formulas, but you need not worry because anyway, you can go back to your formulas. Okay, you are not prohibited in using your formulas whenever you take any form of assessment. Now, last sem, you have learned the derivatives of the hyperbolic functions. There are 6 of them. So sine, cosine, tangent, cotangent, secant, and cosecant. So these are their derivatives. So just like any function, when you integrate the derivative of a given function, so we integrate all of this in here, you will be going back to the original function which you differentiated. And if you look very closely, class, it's really not hard to memorize because you could see here the integral of the sine is the hyperbolic cosine, or the hyperbolic sine has the integral of hyperbolic cosine. The only difference of this with the trigonometric function is this should be negative. But as to the integral of the hyperbolic cosine, it's the same as that of the trigonometric function cosine. For the secant, it's the same as that of the trigonometric function secant also, because when you integrate the hyperbolic secant squared of u, you still have the hyperbolic tangent of u. For the hyperbolic cosecant of u squared, it's the same as that in the trigonometric function. You have negative hyperbolic cotangent. For the hyperbolic secant u, hyperbolic tangent u, the integral is negative hyperbolic secant of u. So negative hyperbolic secant of u. So the only difference with the trigonometric functions is this time it's negative here. Because if we have the trigonometric function, this should be positive. For the hyperbolic cosecant u, hyperbolic cotangent u, the same with the trigonometric function. Your answer is still negative hyperbolic cosecant of u. If it's a trigonometric function, it's just the negative of cosecant of u. The principle you will apply is the same with trigonometric functions. Just make sure that the derivative of the argument of your hyperbolic function should be there, multiplied to it. So this should be du, interpreted as a derivative of the u. If it's not complete and you just need a constant, then you just multiply it with the constant and compensate for the reciprocal of that constant and write it before the integral. Okay? You will see how straightforward are these formulas here in the examples. Okay, hyperbolic sine. So your u in this case, is 1 minus 2x. The du is, of course, derivative of that is negative 2 dx. So you only need to place here negative 2 and you place here before the integral negative 1/2. And that's the reason why you get to see here a negative 1/2. And what is the integral of the hyperbolic sine? That's the hyperbolic cosine. And you just copy the u, which is 1 minus 2x. So now it's negative 1/2 coming from this negative 1/2 which you have introduced here, hyperbolic cosine of 1 minus 2x, which is your u. Do you follow? So it's actually the same as the trigonometric function. The only difference is the signs to the two formulas. The rest of the formulas are exactly the same as the trigonometric function. You can see here you are given hyperbolic cosine of the square root of x. Now, in here, you could see that your u is square root of x. If you differentiate that, that would be 1/2 x raised to negative 1/2. Or you have it here, 1/2 the square root of x dx. So this square root of x that you see below or in the denominator of your hyperbolic cosine actually will be for the derivative of the u in here. So it lacks the 2, so you place the 2 in here. So that's 1/2, so there has to be a 2 before your integral. So the reason why that for the hyperbolic cosine, it's the hyperbolic sine. But since you have the 2 in here, so you have to place it here. You just copy the 2, which you place before the integral, and you just answer the integral for the hyperbolic cosine, which is the hyperbolic sine. Questions?
No.
For the hyperbolic cosine squared of x minus 1, we know that the derivative of the hyperbolic cosine is the hyperbolic sine. So this is it already. Why do you need to have the derivative of the entire hyperbolic function? You need to have its derivative because you intend to use the power rule in here. Your u is the hyperbolic cosine of quantity x minus 1. And in this case, your n is equal to 2. You're allowed to use power rule in this case as long as the derivative of the u is in here. So in that case, it's in here. It's the hyperbolic sine of x minus 1 dx. If you do chain rule here, the derivative of the quantity x minus 1 is just 1 because 1 here will have a derivative of 0. So if you use power rule for the hyperbolic cosine squared of x minus 1, that would be this. The hyperbolic cosine of x raised to 3 over 3 based on power rule. This one is the derivative. The entire expression is the derivative. Now you will have to use the same principle in the fourth example. I'll just scroll up. Okay. In here, if you intend to use the hyperbolic secant of e raised to x as the u, this is your entire u, you will have again n. That is the case. But the thing, class, is the derivative of the hyperbolic secant of u is hyperbolic secant u hyperbolic tangent u. So I'm just saying that if you think this would be using power rule, you cannot because the derivative of the secant alone will be a combination of the hyperbolic secant and the hyperbolic tangent. So in this case, we'll just see whether this hyperbolic secant squared of e raised to x is in itself a derivative of a hyperbolic function. And actually it is. because the hyperbolic secant squared of u is the derivative of the hyperbolic tangent. So you just have to make sure that your u in this case, anyway, it's defined in here, your u is e raised to x. So the derivative of e raised to x is e raised to x. This should be written here, class. There's a typo. E raised to x dx. So this e raised to x here and this dx here will actually stand for the derivative of the u in your hyperbolic secant squared. For you to be able to write the hyperbolic tangent of e raised to x. This is just like hyperbolic secant squared of u, du. So the derivative of the u has to be e raised to x dx. And you can answer the integral for that. Okay, so the hyperbolic secant squared of e raised to x will just have the integral of the hyperbolic tangent of e raised to x because your e raised to x has its derivative here already. Now, number 5 illustrates the use of the identity, which I have shown to you before the formulas for integration. And in those identities, you will see that the sum of the hyperbolic sine squared of x and 1 is the hyperbolic cosine squared of x. Now, you can use either power rule here or you can use this one, the splitting of the hyperbolic cosine in the denominator. So what is important is you have already simplified this to this form because of the identity. Now, if you split the hyperbolic cosine of x into 2, one goes with the x, this one is tangent, hyperbolic tangent of x, and this one is secant, hyperbolic secant of x. And we know that this has a direct integral, and that is the negative of the hyperbolic secant of x. Now, it's based on the 6 formulas that were shown to you a while ago. Do you follow, class? Can you understand? You have any questions? Okay. Now, the number 6 example is already a combination of 2 techniques. One is for the integral yielding an ln. You could see an ln here. So you will have an ln if it's a du over u, meaning the derivative is in the numerator and you have the u in the denominator. So actually what is lacking here is just 2 because the derivative of the hyperbolic sine of 2x is hyperbolic cosine of 2x 2 dx. So you place 2 here and you place 1/2. So you see it's 1/2 the ln of the u, which is the hyperbolic sine of 2x. So it's possible, class, that when you're given an integral to process, you're not only limited to one particular technique. Sometimes it's the hybrid of those techniques that you will use. That way you'll be able to successfully evaluate the given integral. Any questions? It's 4:31. Now the 7th and to the 9th example, I leave to you to read. Should you have any problem understanding, just message me as long as it's office hours. Okay, I can clarify things which may not be clear to you. Okay, so next week you won't have any quiz until, and even this Thursday, I'll be finishing the topics, the rest of the topics for techniques of integration. That way come your exam March 14, the week of the March 14, we will have fully covered, we have fully covered the second module. Do you have any questions? Okay, wait, class, I'll stop sharing.